Jai Hind everyone. So today we are going to start with our next topic of cryptography and network security, final year subject. Till now we have already talked about what encryption is, how we can perform and enhance the security of an open network, how a sender can keep its data secure by performing and using different techniques, and on the receiver side, how receiver can easily decrypt the message and extract the original message out of the coded one. So further going with the same topic, I'm going to talk about today the Elgamal digital signature techniques. As we all know that Elgamal digital signature technique is something which works on the public key crypto system. It is very important and very large scale used technique. Till date, whatever the DES means data encryption standard did, the digital data encryption standard basically taken the 128-bit input and the plain text is of 64 bits. After the computation and permutation methods, it has already been done and it produces a more secure information further. By going through different rounds from round 1 to round 16, we have seen that how the data encryption standard has enhanced the security purposes while information or message is going to be transferred on an open network. An open network is something where already a number of different intruders, the hackers, the third-party persons are available who are always there to just take the information, just to grab the information and finally misuse it. So instead of going through DES, we have talked about that how the RSA algorithm worked for the encryption method, then how there is a Kerberos. Kerberos is used for the authentication purpose where the authentication server is there. In an open network within a particular realm, how the information is securely transferred from one point to another. Maybe it is a client, maybe it is a server, hardly matters. But the thing is how Kerberos enhances the authentication. Because of that also, it is using the ticket granting server as well, which grants the tickets. A ticket is something which particularly informs the person that your duration to communicate is up to this particular extent, and accordingly it goes on. So finally, starting with this Elgamal encryption, let's see that how it is and how it works basically. So Elgamal encryption is a public key crypto system. It uses the symmetric key encryption for communicating between two parties and encrypting the message. This crypto system is based on the difficulty of finding the discrete logarithm in a cyclic group. That is, even if we know GA and GK, it is extremely difficult to compute GAK. So as you know very well, public key crypto system it is. If we are talking about the public key and private key crypto systems, two ways are there. One says that a key which is used for encryption will be the same as it is used for decryption. But the other says that for encryption, we are going to use a particular kind of a key, but for other purpose, for decryption purpose, we are going to use the different key. Or you can say it is one key or two key encryption system. So it is very much clear that it is a symmetric kind of a thing. Symmetric key encryption. It's not asymmetric, it is symmetric key encryption. It is asymmetric key encryption, it is not symmetric. Means it is going to use two different keys for encryption as well as decryption purpose between the two parties. This is based on difficulty of finding the discrete logarithm. Discrete logarithm basically means that how the discrete structures somewhat like the cyclic group, the field, the environment of discrete purpose is going to be used for this encryption method. So let's have an idea about this Elgamal crypto system. In this, first of all, we are going to talk about the various steps one by one which are going to be carried out or which are going to be served through that. Suppose Alice wants to communicate with Bob. Bob generates the public key and private key. Bob chooses a large number Q and a cyclic group FQ. This is the large number Q, that is Q, and a cyclic group, that is FQ. So two persons are there. We are considering it as Alice and Bob. I'm writing it as A and B. They want to start communication like this. So Bob chooses a large number Q and a cyclic group FQ. For the cyclic group FQ, he chooses any element G and an element A such that GCD AQ is equals to 1. Such that GCD AQ is equals to 1. For a cyclic group FQ, he chooses an element G and an element A such that the GCD of these two elements A and G will be equals to 1. So it is somewhat like this, that GCD of A and Q is equals to 1. It is like that. Then he computes H is equals to GA. It is going to use the hash for that. Bob publishes F in such a way that H equals to GA, Q and G are there. All these things are going to be published as his public key and retains A as a private key. So till now, in this step, we come to know that two parties are there. One is Alice, second one is Bob, for example. Public and private keys are going to be generated. Bob generates it, and how it's going to be generated? First of all, it takes Q, then it takes a cyclic group FQ, then it considers the G and A elements in such a way that GCD of A and Q is equals to 1. Then H is equals to GA and F, comma, H equals to GA, comma, Q, comma, G is the public key and retains a private key. This is the thing. Now, the next thing is Alice encrypts the data using the Bob's public key. Alice encrypts the data using Bob's public key. Alice selects an element K from the cyclic group F such that GCD of K and Q is equals to 1. So now it is going to talk about this element K in the cyclic group F in such a way that GCD KQ is equals to 1. So what it is saying? That now the role of Alice starts where the Alice encrypts the data using the Bob's public key. So it is like this, that the element K from the cyclic group F is taken such that GCD KQ is equals to 1. Then she computes P equals to GK and S is equals to HK equals to GAK. So this is the thing, that P is equals to GK and S is equals to HKGAK. She multiples S with capital M. Then she sends the P M into S equals to GK M into S. It is somewhat like this. So these are the steps which are carried out by Alice. This particular set of things are done by Bob. These set of things are done by Alice. Bob decrypts the message. Bob calculates this. S dash is equals to PA is equals to QAK, and he divides this M into S by S dash to obtain M as S is equals to S dash. So while carrying out all these things, we are able to understand what the main logical idea behind the Elgamal crypto system. I want to repeat it once again. Here we are going to use the Bob and Alice, two persons are there. They want to communicate. Suppose Alice wants to communicate with Bob, then Bob generates the public as well as the private key. Certain things will be taken care. They are going to choose a large number Q. Secondly, they are going to use a cyclic group FQ. Third thing, they are going to have the element G and A such that the GCD of AQ is equals to 1. Then finally, they compute the H is equals to GA. Then Bob publishes the F, H equals to GA, Q and G as his public key and retains A as a private key. Then Alice encrypts the data using Bob's public key. Alice selects an element K from cyclic group F such that GCD K Q is equals to 1. Here like this. Then she computes P equals to GK, S equals to HK equals to GAK. She multiplies S with M. Then she sends P with M into S, GK M into S. Bob calculates S dash equals to PAGAK. He divides M into S by S dash to obtain M as S equals to S dash. So this is somewhat like this. Let's start with the another thing. The Elgamal digital signature scheme, basically, it is the Elgamal digital signature scheme is designed to enable the encryption by a user's public key with decryption by the user's private key. The Elgamal signature scheme involves the use of the private key for digital signature generation and the public key for digital signature verification. So there are two important things which we have discussed in this particular slide, that it is going to use the encryption by the user's public key and decryption by the user's private key. Yes, it is very much clear, as in the previous slide as well. I already mentioned that it is going to use asymmetric encryption method. I have already shown that it is going to be a asymmetric key encryption system. Another thing which is highlighted over here is it involves the use of private key for digital signature generation and public key for digital signature verification. Obviously, first of all, the digital signature is generated, then it is used. On the other side is going to be verified. Yes, just because of that, we are saying that it is going to use an asymmetric key encryption method where a key is used for decryption, encryption purpose, and the another key is used for the decryption purpose. Now, this is if Q is a prime number and alpha is a primitive root of Q, then for any integer m, alpha m is congruent to 1 mod q if and only if m is congruent to 0 mod q minus 1. Second point says for any integer I, j, alpha I, it is congruent to alpha j mod q if and only if I congruent j mod q minus 1. So this is something which is very important, that whenever we are going to talk about the Elgamal digital signature scheme or technique, a q is the prime number, alpha will be the primitive root of q, and these two steps will be carried out, where this alpha m is congruent to 1 mod q and this alpha I is equals to alpha j mod q. And these are the two conditions, if and only if. If this satisfies, then we will go for it. Here, the Elgamal key generation is discussed. As with Elgamal encryption, the global element of Elgamal digital signature are a prime number q and alpha, which is a primitive root of q. User A generates a private and public key pair as follows. Number one is generate a random integer capital XA such that XA lies between 1 and Q minus 1. So what it is saying? That as the global element of the Elgamal digital signature, a prime number Q and alpha, this particular thing, prime number Q and alpha with a primitive root of Q. I'm going to highlight all the important points. User A generates public and private key pair as follows. So how it is going to generate it, we are going to see it over here. Number one step, generate a random integer A such that it will lie between 1 and Q minus 1. Another thing is compute YA equals to alpha raised to the power XA mod Q. YA is equals to alpha XA mod Q. Then third one is A's private key is capital XA and A's public key is Q alpha and YA. You can see over here. Moving to another slide, the Elgamal digital signature generation. To sign a message M, user A first computes the hash M equals to HM such that M is an integer in the range which lies within 0 to Q minus 1. A then forms a digital signature as follows. So basically what we are talking about, we are focusing on M, we are focusing on this hash which is M equals to HM. This is something important, that M is an integer in the range and this thing then forms a digital signature. Like this is the condition that how the digital signature for Elgamal digital generation is going to be done. Number one step says that choose a random integer k such that k lies between 1 and Q minus 1 and the GCD of k and Q minus 1 is equals to 1. That is, K is relatively prime to Q minus 1. So it is like that. Second step says, compute S1 is equals to alpha K mod Q. Note that this is the same as the computation of C1 for Elgamal encryption. third step says compute k raised to the power minus 1, means k inverse you can say, mod q minus 1, that is compute the inverse of k modulo q minus 1. Like this. Compute S2 equals to k inverse m minus capital XA S1 mod q minus 1. The signature consists of the pair S1 and S2. So it is somewhat like this, how the amalgam digital signature generation takes place. For the digital generation signature verification, now we are going to see, the first step was the generation of digital signature. The second important step is the verification of digital signature. So any user B can verify the signature as follows. Compute V1 is equals to alpha m mod q. Compute V2 is equals to YA raised to the power X1, S1 raised to the power S2 and mod q. So these two steps are for the digital signature verification purpose. Because over here, as I already told you, the Alice and Bob, two persons are there. Alice starts the communication, it will generate the digital signature. Generation. This is the other party, B. It will verify it. So verification will take place over here. All right. The signature is valid if V1 is equals to V2. Obviously, in this, if V1 equals to V2, only then we can say that it is a valid signature. So let us see that how we can demonstrate this. So it's an example. Let us start with the prime field GF19, that is Q equals to 19. It has primitive roots of 2, 3, 10, 13, 14, 15. We choose alpha is equals to 10. Alice generates a key pair as follows. So Alice chooses capital XA is equals to 16. Then YA is equals to alpha XA raised to the power XA mod Q, that is equals to alpha 16 mod 19 equals to 4. Alice's private key is 16. So Alice's public key is Q alpha and YA, that is 19, 10 and 4. So over here, this is the question. Out of it, group field 19 is going to be taken. Q is equals to 19. These are the primitive root values. Alpha is equals to 10. Like that, it is going to do it like this. You can see over here how the values from this particular question is going to be placed in these given equations. This is the question where all these values are already mentioned in the question. And finally, using these, we are going to take out of our required things. And we will put all those values in the given formulas. Now, suppose the Alice wants to sign a message with the hash value m is equals to 14. So this is the question. Then in that case, what will happen? The Alice chooses k equals to 5 with a which is relatively prime to q minus 1 equals to 18. S1 equals to alpha k mod q equals to 10 raised to power 5 mod 19 equals to 3. K minus 1 mod q minus 1 equals to 5 minus 1 mod 18 equals to 11. And S2 is equals to K inverse m minus capital XA S1 mod q minus 1 equals to 11. That is 14 minus 16 into 3 mod 18 equals to minus 374 mod 18 4. So it is like this. We are doing nothing, but basically what we are doing at the place of Alice, what steps are going to be carried out according to the question. We are just putting those informations and those values into the question. to solve it, and on the other side we are going to take the Bob side and we are going to verify it. So if verification starts, the Bob verifies. Bob can verify the signature as follows. The number one step says V1 is equals to alpha m mod q equals to 10, 14, 10 raised to the power 14 mod 19 equals to 16. And V2 is equals to ya raised to the power x1, x1 raised to the power x2 mod q, 4 raised to the power 3, 4 raised to the power 4, 3 raised to the power 4 mod 19 equals to 5184 mod 19 equals to 60. So these are the two steps which are carried out on the receiver side, that is on the Bob side, to verify this Elgamal digital signature which is already generated. So like this we can say now that signature is valid because V1 is equals to V2. So if we will talk about this NIST digital signature approach, what it says, the NIST has published the Federal Information Processing Standard, that is FIPS 186, known as the Digital Signature Algorithm, DSA. The DSA makes use of the Secure Hash Algorithm, SHA. The DSA was originally proposed in 1991. Several expanded versions of the standard were then issued as FIPS 186-2, FIPS 186-3, and FIPS 186, that is 4. In response to the public feedback concerning the security of the scheme, this large version also incorporates the digital signature algorithms based on RSA and on elliptic curve cryptography. So now last but not the least, we will talk about the disadvantages and advantages of this scheme. So first of all, let's talk about the advantages. There are three concerns when we are talking about advantage, that is security, key distribution, and digital signature. Security says the Elgamal is based on the discrete algorithm problem, which is concerned to be a hard problem to solve. This makes it secure against attacks from hackers. Key distribution, the second point in which the encryption and decryption of keys are different, making it easier to distribute keys securely. This allows for secure communication between the multiple parties. Third is digital signatures, which is the Elgamal can also be used for digital signatures, which allows for secure authentication of messages. On the other side, let's have a look on the disadvantages of this scheme. Three of them are here, which I'm mentioning over here. Three of them are the slow processing, key size, and vulnerability to certain attacks. Slow processing says the Elgamal is slower compared to the other encryption algorithms, especially when used with long keys. This can make it impractical for certain applications that require the fast processing speeds. Second, the key size. Elgamal requires the larger key sizes to achieve the same level of security as other algorithms. This can make it more difficult to use in some applications. Vulnerability to certain attacks is Elgamal is vulnerable to attacks based on the discrete algorithm problems such as the index calculus algorithm. This can reduce the security of the algorithm in certain situations. So by this, I have completed this topic where we have talked about what is Elgamal digital signature technique, what are the ways that how two parties can start communicating with each other using an asymmetric key encryption method, in which public key and private key both are used for encryption and decryption purpose respectively. Finally, after that, we have talked about how the digital signature generation will take place on one side and how the digital signature verification will take on the other side. And then the most important thing, the advantages and disadvantages of this scheme. Thank you.